exact amount of current that it encloses. Right? It's a little bit like magic, but actually it's not magic because all B fields originate from current. So if you know the B field, you also in some sense know what current is. Okay, so this integral circle sign, once again this circle sign, don't ever be confused when you see it. The circle just means closed. Okay, in this case it's a one-dimensional path, it's a closed loop. For Gauss's law, it's a two-dimensional path, so it's a closed surface. Okay, and you guys will not encounter a triple integral of a circle, but if you ever, I mean in this course, but if you ever encounter it outside this course, that's a closed volume. Okay, and yeah, closed volume requires you to think about 4 dimensions instead of 3 dimensions. Okay, but basically this concept scales up to any number of dimensions one drops off. Right, don't ever, right, that's all this circle means. Okay, so if I'll take B and dot ds, where ds is the differential element along the path I want to integrate, right? Integrate it along a closed path. I'm going to get mu naught times I, where mu naught is the permeability of free space. That's a fundamental constant, also found at the back of your exam. You don't have to memorize it. And I is the total current enclosed. Okay, the total net current enclosed. And by the total net current, I mean I1 plus I3 minus I2. Okay, I hope no one gets confused why I2 has the opposite sign compared to I1 and I3. Right, because I2 is going into the page, but I1 and I3 is pointing out of the page. Right? Yeah. Right, maybe a bit more confusing is you might ask me, how come it's not minus I1 minus I3 plus I2? Does anybody want to answer this question? Or guess the answer to this question? How do I know it's I1 plus I2 minus, sorry, I1 plus I3 minus I2, not minus I1 minus I3 plus I2? Okay, the dot and the x has something to do with it, okay, but how do I use that to figure things out? Okay, the answer is once again your right hand. Okay, so if you point your fingers, okay, this time you start from curling fingers. If you point your fingers in the direction along the path, the direction in which your thumb is pointing tells you which direction is the positive sign for the current. So in this case, if my fingers go along the path, I notice my thumb is pointing out of the page, right? So out of the page is positive. So I1 and I3 is positive, or rather I1 and I3, I'm not including any negative sign in front of it. But I2, I will include a negative sign because it's pointing in the other direction. Okay? Okay, so then we move on to another set of concepts which has to do with something called the electromotive force and inductance. Okay, so can someone tell me what is the units of electromotive force? Oh, very good, V. Okay, right? Some people get confused because they hear force and they don't think of newtons. Okay, but electromotive force is a very old word, right? But it refers to electric potential. Okay, it refers to voltage. Doesn't refer to force in any sense. Okay, and it's given by d phi over dt, where phi is what is known as the magnetic flux. Okay, and the magnetic flux is basically like the electric flux, right? Electric flux is the E field multiplied by the area. Similarly, magnetic flux is B field multiplied by the area. Okay, and the electromotive force, right, is given by the rate of change of the magnetic flux. Okay, why is this the case? Why is it that when electromagnetic flux change with time, we suddenly have a potential or voltage difference? Right, that's just the way nature is built, right? I mean, science can describe how, it can't explain why. Okay, to explain why, you need to turn to philosophy or religion or something, right? But the scientific law is just like that. People did a lot of experiments, they find that, hey, this is the way it works. And people have exploited this to create machines, right? Things that can generate energy, or ways to convert, energy from like the wind, or the water to stop electricity, right? So this is one important equation in that process. Okay, so there is also this important law called Lenz's law, right? Because so far I've told you that the magnetic flux, when the magnetic flux changes with time, there will be an electromotive force, aka a voltage drop. right? This voltage drop will of course lead to current flowing, right? As long as your wire has some resistivity, it will lead to current flowing. But your question to me might be, where is this current flowing? In what direction does this current flow? And that's answered by Lenz's law. The current will always flow in such a direction that the magnetic field created by the current opposes the change in magnetic flux. And once again, why is that so? That's just the way it is. Okay, that's the laws of nature. Right? So once again, Lenz's law tells us that when this EMF is created, the current that will flow as a result, okay, it will flow in only one specific direction. That direction is determined by, that direction will be the direction such that the magnetic field that it sets up opposes the rate of change of magnetic flux that produces it. And that's a lot of English words, that's a mouthful. I don't really expect you to completely get it. That's why we have an illustration over here. Okay, I want you to pay good attention to this illustration because we are actually going to use this as one of our problems. Okay, we're going to revisit it in one of our problems. Okay, so in the problem that you'll see later in the tutorial, I have a uniform magnetic field and I have a loop of wire. Okay, this is a rectangle loop of wire. There's nothing inside, it's just a loop of wire, just like you take a wire and bend it into a square. Now I am pushing it into the magnetic field. Okay, what happens? Okay, so the scientists that first experimented with, they were very surprised to experience a force. You know, when they push, like, I mean, it's just a magnetic field and I'm pushing in a wire. The wire is not charged. Why am I experiencing some sort of force? And it's not electric field either, it's a magnetic field. Why am I experiencing some sort of force? Okay, so that's how they discovered this law. So let's see how these laws result in a force. First of all, let's notice that magnetic flux is changing. Okay, magnetic flux is given by, right? In this case, it's given by just the magnetic field dot the area, right? Just like your electric flux was given by electric field dot the area. The B field refers to the B that is pointing into the page. Okay, please don't confuse it with this B here. This B refers to side B of the square. Okay, and then your A refers to this area, right? At this instant in time, the area is given by the shaded portions of this diagram, and it's pointing. What direction is it pointing in? Right? We can treat it as it's pointing in the outward direction. Okay, so right, B dot A. Okay, we treat it as it's pointing in the outward direction. Okay, let's see, the sign of phi, shouldn't affect the result. Okay, because at the end of the day, the direction of the current will be dependent on Lenz's law. It doesn't, right? It doesn't depend on the sign of EMF. Okay, so it's the magnitude of EMF that we care about. So I can even put a particular sign. Okay, so the magnetic flux. Okay, the magnitude of the magnetic flux. As I push this square of wire into the magnetic field, can someone tell me, is it increasing or decreasing? Who thinks it's increasing? As I push the loop of wire into the magnetic field, is the magnetic flux increasing with time or decreasing with time? Who thinks it's increasing? Who thinks it's decreasing? Okay, it's got to be increasing, right? Because the more you push it in, the more, right? An instant in time later, it will look like that, right? And then, right, there's even greater shaded area over there. Sorry, it doesn't explain in science. That's my bad drawing, okay? But you can see a greater portion of the wire, right, has magnetic field passing through it, right? So the magnetic flux increases. Okay, and note that this magnetic flux is produced by a magnetic field pointing to the page. Now, Lenz's law says, okay, this formula says that thanks to me, thanks to my itchy fingers, pushing the wire into the magnetic field, right? Because phi is changing in time, d phi over dt is non-zero, therefore there will be a potential difference. Okay, but it doesn't tell me what's the current that will be induced by this, or rather what direction the current due to this potential difference will flow. And there are two possibilities. The current can flow clockwise, or the current will flow anti-clockwise, right? It's just a loop of wire, it flows clockwise or anti-clockwise. So would someone like to explain, or try to explain, Why would it flow clockwise or why would it flow anti-clockwise? Who thinks it flows clockwise? Who thinks it flows anti-clockwise? Nobody wants to give a guess? Okay, who thinks it flows clockwise? Last chance. Who thinks it flows anti-clockwise? Okay, so hold on to your answers. Even if you don't put up your hands, you can guess something in your head and see if you're correct. Or try to reason it out, okay, right? Guessing is last resort, right? Try to reason it out. Okay? Yeah, by the way, there's a tip for the upcoming quiz, right? Never leave an answer blank, right? You always guess. You really don't know if you guess, right?
I didn't know that.
Okay, sorry, I'm sure it's obvious. Anyway. Okay, but maybe what's less obvious is you'll be surprised how many people leave their exam answers completely blank. You know, when you leave your exam questions blank, it's as good as, it's like an MCQ where you don't bother to even try or write, right? Because even if you write something that's partially correct, you get partial credit.
What if you have nothing in your mind at all? That's why you leave it blank. I totally don't know anything on the topic. You can just write like the formula inside, like then like try your luck. Like, you write all the formula inside, all of it is correct.
Okay, so well, if you write all the formula, the grader will catch on to what you're doing, and you're not likely to be awarded marks. Yeah. So you've got to it's got to be an educate. I mean, but writing one formula, right, or writing a formula and trying to work something out is better than nothing at all, right? At least you're giving yourself some chance. Okay, so the advice wasn't that obvious. It was obvious for the quiz. Okay, maybe not so obvious for final exam. Okay, coming back to this. Okay, right. Basically, I was asking you guys to guess the current is counterclockwise or clockwise. Okay, and the answer we need to figure out using Lenz's law. Lenz's law tells me that the current will flow such that the resulting magnetic field will oppose the change in magnetic flux. Okay, so note that the magnetic flux is increasing due to a magnetic field pointing into the page. Okay, because this group is seeing more and more of a magnetic field pointing into the page, you can say that the laws of physics dictate that its instinct is to create a magnetic field that points out of the page in the opposite direction. And what will produce a magnetic field that points out of the page is a counterclockwise current. Okay, so you can use your right hand again and see. Okay, to produce a magnetic field out of the page, you need a counterclockwise current. And that is why your current is going to be counterclockwise. Okay, and once you have a counterclockwise current, actually later on in the problem, okay, maybe not here, later on in the problem we'll see why you experience a force, right? Why this group of wire actually experiences a force. Okay, the reason is because of, once again, F equals IL cross B. This I is going to interact with this B to give you an F that pushes the wire in a certain direction. Okay? Okay, for now, okay, and by the way, groups of wire is something that is a very useful device in electrical engineering. Like, I'm not sure if you guys have heard of power transformers that transform, you know, a very big current to a very low current, or very big voltage to a very low voltage, and vice versa. Right, so loops of wires, they are very useful, and actually we are going to see why later. Okay, and basically when you have a lot of loop of wire, one of the basic properties that govern it is this property called inductance. Okay, so a resistor, right, is something that opposes the flow of, opposes the flow of current, right? So if you have a very big resistor, you need a very big voltage to generate a current, right? So and capacitance, right, capacitor, which you guys learned last week, right, that's related to charge and voltage, right? The bigger the capacitance, what does it mean? Okay, I want a lot of charge stored. Do I want a bigger capacitance or a smaller one? Yeah, I see you nodding. Okay, very good. You want a bigger one, right? Because Q equals CV. For a given voltage drop, you get a much bigger charge separation of a bigger capacitance. So inductance is another fundamental property of circuits, right? But this inductance doesn't tell you about charge. It tells you about magnetic flux. Okay, so for a given current, you will set up a certain magnetic flux. Right? If your inductance is big, it means for very small current, you will set up a very big magnetic flux already. And magnetic fluxes, they are useful for a lot of things. You know, they are useful as a way to store energy in a magnetic field, as a way of converting voltages, right? And generally just very useful. Okay, and by the way, inductors and capacitors, they are not just devices, they are properties of the things that we put on our circuits. You know, so everything has a capacitance and inductance and capacitance. And one more thing that you guys won't learn about is called resistance. If you do something that was discovered relatively recently or demonstrated relatively recently. Okay, so that's why in a lot of cases we have things called parasitic inductance, parasitic capacitance, because we actually don't want them to exist. Okay, so right, it's a fundamental property of our circuit element. Okay, okay, so I have an unofficial formula sheet number 2, but I don't think you guys need this. Okay, I don't think you guys, can someone let me know? You guys tested on electromagnetic fields, time varying electromagnetic fields. Is it part of the syllabus?
Oh, we don't know. We hardly read though. I'm not gonna lie, we really don't know.
Okay, okay, now I will figure it out. Okay, very easy, very easy. Someone tell me, okay, someone please help us out to look at the tutorial questions. Can you tell me, is this question covered in the tutorial? 15 milliwatt helium neon laser. You are being asked about the maximum electric and magnetic field. No, right? Yeah, okay, so don't worry about it. Yeah. So today only 4 questions? Oh, okay, great. Yeah. Okay. So any questions before we begin today's tutorial questions? Okay, so first question, 2 long parallel wires. They have a certain mass per unit length and they are supported in the horizontal plane by strings, 6 centimeters long. Each wire carries the same current, I, causing the wire to repel each other so that the angle theta between the supporting strings is 16 degrees. Are the currents flowing in the same or opposite direction, right? The answer is opposite. So I won't ask you the answer, right? But I'll ask you why is it opposite? What tells you that the answer that the current is flowing in the opposite direction?
Repelling.
Repelling, very good. Okay, excellent. Okay, right, repel. So, right, we can see that these rods, they are some distance apart, right? Meaning they are repelling. And currents flowing in the opposite direction repel each other, so the answer must be opposite. Okay, that's part A. And now part B, which is more mathematically involved, determine the magnitude of each current. Okay, so let's go about this. Okay, so once again, right, so we went through this in a formula sheet, right? So actually going through the formula sheet, it wasn't right, it wasn't only a prelude to our tutorial questions, it actually forms important parts of our answer as well. Okay? Since we just went through this, I won't go through this again, but you know, if you guys forgot something or want to clarify something or just want me to go through it again, no problem, just let me know. Okay? So basically, since you have since you have wire 1 setting up a B field and IL cross B producing a force to the right, you will notice that wire 1 produces a force on wire 2 to the right. You can do the same for the force that wire 2 exerts on wire 1 and you find that it's to the left. Okay, so it will repel. Okay, now this will produce these 2 repulsive forces, A, F, E. Right, I've drawn in my free body diagram. You guys can go to physics A or free body diagrams. You guys have seen it before, right? So in this case, right, it's a mix of, right, it's a bit of classical mechanics mixed with electromagnetism, right, mixed with electrostatics, right, because this F is due to magnetic force. But this mg is something you have encountered before, right? It's the weight, right? It's the gravitational pull on this, right, this rod. Okay, and somehow this force and this mg is counterbalancing the tension in the string. Okay, not somehow. Okay, the fact is, these 2 forces are being counterbalanced by the tension in the string. That's why these rods are not moving. Right? If the string is weak and the string cannot withstand this tension, then the string will break and the rods will just fly apart. Okay, but apparently it doesn't break. Okay, it's strong enough to hold it. That's why we have this static picture. That's why these rods are equilibrium, right? And we have a problem to solve here. Okay, the angle, as the question tells us, between these 2 strings is 16 degrees. We are being told the length of this string. Okay, so what should we do in this problem? How to tackle this problem? So what's the next step in this problem?
Find the force.
Okay, I hear right angle triangle, I got find the force, you guys are going ahead of me. Okay, right? Just using FB and MG and T. What do we expect them, how should we write it mathematically? How do we put it together mathematically?
A resultant.
Resultant force, okay. Resultant force is what? Very good, okay, I heard zero somewhere, okay. Resultant force is 0. Okay, very good. So what you want to do is this is a two-dimensional problem, right? I want to break it into x and y. You expect all the forces in the x direction to sum to 0, and all the forces in the y direction to sum to 0. Okay, so what are my forces in the x direction? Okay, let's go through these equations line by line, make sure we really get there, right? T cosine theta, where did that come from, right? That's the tension in the string, and I projected it along the horizontal or vertical direction. T cosine theta projects the tension along which direction? Is it this direction, or is it is it this direction, or is it, I guess we could talk about this direction. These are the only possibilities, right? Hold on, let me see. Oh, sorry. Don't ignore that. Okay, this is, I got it wrong there. T cosine theta, are you projecting it along this direction or along this direction?
The down one.
What do you mean by the down?
The y one.
This is option A, this is option B.
V.
Okay, who thinks the answer is B? Who thinks the answer is A? Okay, the answer is A. Okay? It's tricky because we are very used to thinking of cosine theta as projecting into x direction, right? Projecting in the horizontal direction. But that depends on your angle. Okay, in this case, theta is defined as this angle. Okay, and let's all remember that cosine theta is adjacent over hypotenuse, right? In this case, adjacent is this, right? And hypotenuse is the capital T, right? It's this arrow. Okay, so T cosine theta basically gives you the vertical component of tension. Okay, and let me write it very clearly here. This is T cos theta. Any questions? Okay, anyone any doubt? Anyone disagrees?
Correct.
Okay, it's tricky, it's tricky because we are very used to cosine theta on being horizontal. Okay, but you got to be careful because they might choose to label the angles very creatively to confuse you, right? Well, not to confuse you, no, it's just that, some angles they are more convenient. It's sometimes more convenient to label certain angles than other angles. Okay, and it must counterbalance my weight, right? Agreed or not? Right? MG is pointing in a downward direction. FB is not pointing in downward or upward at all. Right? So T cosine theta must balance my MG. Okay? And similarly, along the horizontal direction, T sine theta must balance my FB, right? My magnetic force. Okay? And having these two equations, right? Now that I've established these two equations, I can do things with them. I still don't know how to solve it, but I can stare at them and wonder to myself. But actually, here I already got quite a bit of partial credit already, right? If this is a final exam. And then I can stare at this and think of the stuff I can do. And one of the things you can do is you can divide one equation by the other. Right? There's only so many ways you can manipulate two equations. You can divide, you can add them together, you can subtract them, you can multiply them together. Right? Multiplying is not advice, right? If you multiply them, it seems to be even more complicated. Okay, but if I divide them, what happens? Right? I get to cancel capital T out. Right? I get to cancel, actually, if I divide FB by MG, I T sine theta divided by T cosine theta. Here I can cancel out one unknown. Right? Capital T is an unknown, I got to cancel it out. And then I end up with the equation FB over MG equals tangent theta. But I'm being told in the equation that theta is 8 degrees, right? Because this angle is 16 degrees, and this theta, I hope everyone can see the Z. Right? So there's some geometry here also. I hope everyone can see the Z, right? This theta is equals to this. Okay, therefore theta is 8 degrees. Okay, anyone has any objections, please let me know. Okay, very normal to have a lot of questions. Okay, so in that sense, I actually know that FB over MG is tangent 8 degrees. Right, and that's great. I reduce the number of unknowns in this equation by a lot. Okay, now what is the value of capital B? Okay, the reason I need to know the value of capital B, let me erase this to make it clearer. The reason I need to know the value of capital B is because I need to figure out FB, right? Remember FB is ILB, right? IL cross B, which magnitude in this case is I times L times B. Right, so I need to figure out what is capital B. But capital B is given to me by my formula sheet. Okay, and once again, please do not just memorize it, right? Please try to be familiar with the derivations, then you're more comfortable with knowing when to apply what formula. Okay, so this is the formula that we get thanks to Ampere's law. Okay, mu naught I over 2 pi r. Basically, your B field decays as 1 over r, right? When you move further and further away from the current I. Okay, so if I were to substitute in the quantities that my problem gives me, right? There's 0.06 over here, right? And sine 8 degrees. Where did this come from? Okay, it actually comes from this r over 2. Okay, right? It basically comes from right? We basically want the distance between these two rods, right? The distance between, sorry, my apologies. We actually want, we want the, okay, hold on, the B field mu naught I naught over 2 pi r. We actually want, oh, sorry, I got confused. Yeah, 2 pi r. This r, okay, is the distance between these two rods, right? Here we decided to be a bit creative and write it as 4 times r over 2. I mean, that's the same as 2r. Okay, so why they did this mathematical split, you know, because I'm not the one that prepared this slide, right? Why they did this mathematical split is for convenience. Okay, now I can see it's for convenience because instead of calling this 2r, I can call this 4 times r over 2. And r over 2 is this. Okay, r over 2. Okay, and how do I obtain this length? Right, it's by 0.06 times sine 8 degrees. How do I see that? Okay, 0.06 is the length of my string. Right, so this is 0.06. Okay, and let's remember that sine 8 degrees, right, is equals to opposite over hypotenuse, right? Opposite refers to this r over 2, right, which is opposite 8 degrees, this 8 degrees, right? Opposite refers to r over 2, so this is r over 2. Hypotenuse refers to 0.06 meters. Okay, let me know if you don't follow. Right, therefore r over 2 can be replaced by 0.06 times sine 8 degrees. Does that make sense? Or did I lose someone somewhere? Okay. Okay, so once you have the expression for, sorry, does it make sense? Anyone has any, or should I go through that again?
No, it makes sense.
Okay, makes sense. Okay. Okay, so what we can do is, now that we have expression for B, we can substitute that into our expression FB over MG equals tangent 8 degrees. Right, because FB is just ILB. Okay, MG is MG. Okay, but ILB is this entire expression that I copied and pasted from here. Right, that's all that it is. Okay, right, I substituted, right, or rather I copied and pasted the B. Right, this is B. Okay, this is ILB. Okay, except for the extra factor of I naught and except for L, everything is copied and pasted from the top expression for B. Okay, and I set it to be equal to tangent 8 degrees. And if you look at this, formula, right? If you look at this equation, okay, it looks like a big chunk of math, but every single quantity there, you already know the number because the formula, because the question already told you what the number is. You know what is L, right? It's just 0.06 meters. Okay, you know what is I naught, right? You know, right? Mu naught is a fundamental constant, you know, right? Everything else you know, okay? Hold on, sorry. Actually, it doesn't matter if you know what is L or not, because L actually cancels out numerator and denominator. Okay, so you set it to be equal to tangent 8 degrees because of this equation over here. And the only unknown is I naught. Okay, the only unknown is in this equation is I naught. So you just rearrange everything with I naught on the left hand side. Okay, let me clear first. With I naught on the left hand side and everything else on the right hand side, and you solve for I naught 67.8 amperes. Okay, any questions? Any part? Does anybody want to go through any part again? Okay. Okay, so the first step, remember the first step is always the hardest to take, right? Right, like someone had a comment just now, it's so hard to know when to start. Yeah, that's very common. Right, the first step here is you're going to balance the forces out. Right, and the way you know this is by seeing, hey, you know this is a free body in equilibrium, we've got to balance the forces out. Okay, if there are no questions, then we're going to move on to question 2, right? On something that's very familiar to us, right? Because we went through part of it in the formula sheet. Okay, I have a rectangular loop with resistance R and it has n turns. Okay, so do note that this is not one loop of wire, it's a coil of wire. It's a rectangular coil of wire. I've coiled it so many times. Okay, I've coiled it n times. It has resistance R, right? And it's of length L and width W. Okay, that's just how big my square is. Okay, the loop moves into a uniform magnetic field B with a velocity V. Right? What is the magnitude and direction of the resultant force of the loop under the following conditions? As it enters the field, as it moves within the field, as it leaves the field. Okay. So let us first answer the question. Why is the force, as it enters the magnetic field, why is the force acting to the left? Okay, let me see. Do I have an illustration? Yeah, let's not go through the math first. Let's just answer the simple question which we can do by pointing on fingers, right? Why the force exerted on this loop is pointing in this direction? Okay, why is it pointing to the left? Why not to the right? Why not up? Why not down? Why not into the page, out of the page, or at some funny angle? Okay, so let's revise what we saw in the formula sheet. Okay, first of all, as my loop enters the magnetic field, my magnetic flux, due to the magnetic field pointing to the page, is increasing or decreasing? It's increasing, right? Okay, so as it enters, it's increasing. Okay, since it's increasing, okay, and we need to remember that the magnetic flux is due to a magnetic field pointing into the page, then the natural way for current to flow is such that the resulting magnetic field will point out of the page. So current will flow in a counterclockwise direction so that the resulting magnetic field opposes the change in magnetic flux. Right? This magnetic flux is due to a magnetic field pointing to the page. Right? So the loop of wire is rebellious, right? That's Lenz's law, right? Loop of wire is rebellious. It will produce a current that produces a magnetic field pointing out of the page. Okay, so I know that my current is going to go this direction. We right counterclockwise. Okay. Now I have a current. Okay, I have a current moving in a magnetic field. I need to use my formula F equals IL cross B. Okay, let us put out our right hands. Okay, and extend our fingers. Okay, first index finger is always in the L direction, which is the direction the current is flowing. Let it point up. Okay, then my middle finger, should it point into the page or out of the page? Into the page, very good, because the B field is pointing into the page. And notice that your thumb, okay, is pointing to the left. Right? Therefore, my force is indicated by the direction of this yellow arrow that I drew just now. Okay, it's pointing to the left. Okay, so pushing the loop into the magnetic field, you will feel a resistance, right? Which might be quite mysterious. You know, oh yeah, I just have a static magnetic field there, you know, and I'm pushing a simple loop of wires through it. How come I feel a force, you know, like a ghost is struggling with me, you know, with this wire, right? Is there some unseen presence, you know? Right? No, it's just electromagnetism. Right? It's just Lenz's law. It's just because a current starts flowing in a wire and the current interacts with the magnetic field to produce the force. Okay, so that is why the answer is actually to the left. Okay? Any questions on this?
L is pointing upwards because the current is moving upwards.
Okay, the question, actually it's a really good question. Okay, L is pointing upwards because the current is going upwards, correct? The current in this arm is going upwards. Okay, and I really like that question because it reminds me to say something. Right, this current is pointing upwards. Okay, you guys might be asking, hey, but the current is pointing downwards here. So why isn't it downwards? Okay, exactly, it's not inside the magnetic field. Simple as that. Right, it's not, it hasn't seen the magnetic field yet. Okay, and some even more astute people ask me, well, what about these currents left and right? Why not pointing left and right? And the answer is you can repeat the process for left and right, but the force exerted on this guy and the force exerted on this guy will cancel out, equal and opposite directions. So I don't even discuss it at all because they cancel out. Okay, but you'll find that for one of them, it's actually we can do it real quick. For this upper guy, okay, L is this direction, right, to the left, okay, and B is once again into the pitch. I'm going to get a downward force for the top element. Okay, so the top element actually experiences a downward force. The bottom element actually experiences an upward force, but they cancel out. You know, so it's, yeah, right, cancel out equals 0. Okay, so very good question. What about the other arms of the current? Right, right, that's why it's good to ask questions. Okay, any other questions? Okay, if not, then let's go about actually calculating the magnitude of this force. We know the direction of this force. What is the magnitude of this force? Okay, and to begin with, let's calculate the electromotive force. Okay, electromotive force is the voltage drop due to the rate of change of magnetic flux. How to calculate the rate of change of magnetic flux? Very simple. The expression for magnetic flux is just B multiplied by the area, right? B field multiplied by Wx. W is the length of this rectangle, right? And X is the width of the rectangle inside the field. So W times X gives you the area inside, area of the magnetic field. Right? When you multiply that by B, you just get the magnetic flux. Okay, how to calculate rate of change of magnetic flux? Put this inside d over dt. Right? And notice that B is constant and W is constant, so you can take them outside, which leaves you with dx over dt. Right? dx over dt is just speed. Right? Speed is the rate of change of distance. Okay, or velocity is the rate of change of displacement. But here we are dealing with scalar, right? So speed is the rate of change of distance. Okay, so you have mvw over here, you have dx over dt over here, and that's nvwv. Okay, now I know my voltage drop. How to calculate my current? Using the good old rule that you guys are no doubt extremely familiar with, right? Voltage equals resistance times current, which in this case I rearrange to say current equals voltage over resistance, right? Please don't be alarmed that, or please don't be thrown off by the fact that voltage here is represented by epsilon. You can call it any symbol you want, right? In fact, if you want to call this V, nobody's going to stop you. Right? But by convention, we always call EMF epsilon. Okay, not to be confused with, okay, well, and not to be confused with any other epsilon, okay? You will no doubt encounter many other epsilons. Let's say, for instance, epsilon naught, you know, the permittivity of free space. And later on in quantum, we will have another variable that gets represented by epsilon. Okay, but right, there are only so many symbols in the world, right? So it's not surprising that it is some. Okay, now this epsilon is simply given by MVWV, like we calculated above here. So we have an expression for the current, right? MVWB divided by R. Okay, now I have an expression for the current, and I know the direction is flowing in. Okay, all I need to do is to calculate the magnitude of the force, which is ILB. Okay, so since we have already used the right hand rule to calculate the direction, we don't need to worry about the vectors now. We just need to calculate the magnitude. Right, and since L is perpendicular to B, you just need to multiply them together. Right, remember for cross product, the magnitude is actually vector magnitude of vector A multiplied by magnitude of vector B times sine of the angle between them. But because L and B they are at right angle, sine 90 degrees is just 1. So it's literally just the two magnitudes of the two vectors multiplied together. Okay, so you have NILB. Okay, and please do not forget this N over here. Okay, why do I have this N over here? Can someone tell me? How come I just randomly, I mean F is IL cross B, right? How come I change the formula? What gives me the right to change the formula? Oh, very good. Okay, N terms is a very good start to the answer. Why? Why does the fact that it's N terms matter?
Because the more, then the thing will be stronger.
More than thing also the stronger is very good on the path, but it's still not completely clear yet the answer. Okay, force is IL cross B. But is that the force on I mean that's the force on one. Exactly, that's the force on one turn. Right? Because I is the current flowing through one turn. Right? If I consider all of the turns, each turn contains or carries I. You know, and each turn therefore experiences the force IL cross B. Okay, so you want to find the total cross on this you know, square loop with so many turns, you got to multiply by n. Okay, so I didn't change the formula, I didn't adjust the formula. I simply accounted for the fact that IL cross B corresponds to the force of one element by n elements here because I turned it so many times. And as a result, you will see over here that you have n squared. Okay, and this is the beauty of this is why electrical engineers like coiling things together. Okay, you don't just enhance things by a factor of n, you enhance it by a factor of n squared. You get one factor of n thanks to up here, right? The EMF induced. By the way, I forgot to ask you guys about this. Why is there a factor of n here? But it's the same answer. Every time your B field passes through one loop, that's basically one unit of phi, you know. Right? So if it passes, it cuts through n loops, that's n phi, because the phi's correspond to the magnetic flux for one loop only. So you get n square enhancement in your force thanks to using the loop, right? Not just a factor of n, you know, or square root of n or whatever, you get n squared. That's a very big enhancement, right? Just by turning the wire, right? You don't have to increase your current, right? You say, oh, increase current, my power generator is not strong enough. You don't have to increase your current, you just need to coil the wire together. Okay, that's why coiled wires are so common, you know, in our field. Okay. Okay, and okay, so that's the end of part A. We have determined the direction of the force, we have determined the magnitude of the force. Any questions? Okay, if not, let's move to part B. Part B, you guys already know the answer, right? You are going to experience no forces. Okay, right? And the simple reason is because when the loop is in the magnetic field, there is no change in magnetic flux. Okay, magnetic flux does not change as a function of time. Therefore, the phi over dt is 0.
But in this case,
right? And there is no current to speak of, so there's no force to speak of. Okay, please don't get confused and say, oh, the force in this arm balances out the force in this arm. Well, technically that's true, but the force is 0, you know, right? Everything is 0. Okay, and for part C, I'm going to leave it to you. Okay, I'm going to leave it to you to try out yourself because it's exactly the same as part A. Okay, it's exactly the same exercise as part A. You need to apply Lenz's law to figure out that the current is traveling in a clockwise direction. Then you need to apply your right hand rule to figure out that the force is pointing to the left. Okay, so once again it's pointing to the left. Okay, you'll find that the magnitude of the force is the same as part A. Okay, question 3. Okay, so any questions for question 2 before we move on to question 3? Okay, so question 3, a conducting rod of length L moves with velocity v parallel to a long wire carrying a steady current I. Okay, the axis of the rod is perpendicular to the magnetic field. Okay, and the near end is a distance r away. Okay, so r is this distance between the wire and the near end of the rod. We want to show that the magnitude of the EFF induced in the rod is given by this. Okay, and as you guys know, electromotive force is just d phi over dt, right? But there is a complication here, right? The complication is that the B field is no longer constant in position. Okay, the B field varies as a function of r, okay, or as a function of x. If I call this the x direction, the B field varies as a function of x. That means I cannot simply calculate d phi over dt anymore, where phi is b times w times b like the last time, right? Okay, so what I need to do here is actually need to consider a very small part. Okay, figure out the contribution of the EMF of this very small part and add up all the small parts together. And that's because the B field is not uniform. Okay, so this is a problem that calls for integration. Okay, so here, first of all, you want to know what the B field is, right? The B field is given by mu naught I over 2 pi r, or mu naught I over 2 pi x. Okay, and what is the contribution of this very tiny element to the overall EMF, right? The induced EMF is given by this dV, right? Remember, this d is not a separate variable on its own. It corresponds to a very small increment, right? Or very small contribution in d. Okay, it's given by BLV. I'm just taking it from the previous question, right? Remember, previous question, the EMF is BWV. Right here we change W to L, but that's just me renaming, not me, but the question renaming its variables, right? So BLV. Okay, right? And in this case, B is not constant as a function of x, so I have no choice. I can only consider a very small element in the x direction, and then later add it all up. So I'm going to take B, this is B, okay, this is B. Where is L? L is the x. Okay, the x is the length of our infinitesimal element. Infinitesimal means okay, and V is V. Okay, and then once I have this expression, I want to do the integral. Right? I just want to add this integral sign, and I want to integrate from r to r plus L. So if you have worked all the way until this, here is where all of the physics ends. Everything else is mathematics. Okay, then you need to do your integral, and that's an important part of physics, that's an important part of engineering math. We can't get away from it. Right, but what I can tell is the physics reasoning ends at this point. Okay, it doesn't mean what's after this point is not important. Okay, but the physics reasoning ends here. Okay, and I hope no one is confused about why we're integrating from r to r plus L, right? Because you are starting from x is equals to r. Okay, and you're integrating to x is equals to r plus L. Okay, where this is 0. Okay, why is this 0? Because 0 is our, right, is the location where our wire is, right? So that's why it's 0. Okay, so I have a pretty easy integral to integrate. I'm quite happy to see. Right, it's 1 over x, I'm integrating 1 over x. The integral of 1 over x is just natural log. Yeah, okay, so this location of the wire is 0 because of this formula. This formula B equals mu naught I over some pi r presumes that r equals 0 is the location of the current. Okay, so okay, the next part of the question is also quite straightforward, basically they ask you which end of the rod is a rod with higher potential. Okay, the answer is that. Okay, so can someone remind me, current, does it flow from higher potential to lower or lower to higher?
Higher to lower.
Exactly, higher to lower. Right, so the way you can, right, the way you want to study this is by studying how the current flows and then how it pushes the charge. Okay, so basically what we see is, if you have an electron, okay, if you have an electron in this rod, right, and this electron is being forced to move in the upward direction because that's where the rod is moving. Okay, the force exerted on the electron is in such a way that the electron moves to the right. Okay, if you do Q equals V cross V, which you can do real quick, V is pointing upwards. Okay, my index finger is pointing upwards. And then B, right, the B field is pointing into the page, right? Because if you do your right hand rule for I, you see that the B field points into the page. Okay, therefore my thumb is pointing to the left. But Q has a negative sign, right? So I flip the direction. The force is pointing to the right. So all your electrons get driven to the right end of the rod. Okay, and as a result, your right end of the rod is negatively charged. Your left end of the rod is positively charged. Okay, so as a result, the higher potential is going to be on the left end. Okay, and this is the explanation. Right, in words, right? Exactly what I've just said, right? But written in, written in formal sentences. Okay. Okay. Then question 4. Okay, question 4 asks us to calculate the inductance. Okay, so the inductance, right? As you recall, inductance is given by phi over I. Okay, just like resistance is given by V over I, right? Resistance is voltage divided by current. Okay, inductance is magnetic flux divided by current. Okay, so to calculate the inductance of this toroidal loop, I want to calculate my magnetic flux through this, right? Through this donut, right? This squarish donut. Okay, right? This donut is square cross section. Okay, and then I'll divide it by the current. Okay, so to do this, you want to use Ampere's law. Okay, right? So, right, we talked about Ampere's law. If you were to draw a line, right? And by the way, this line is just like Gauss's law. It doesn't have to be Gauss's law doesn't have to be a real surface. It can be something you imagine. This line can also be just an imaginary line. If I were to draw this line, okay, right, around a certain region, I expect that, and I integrate the B field along this line, I expect the result to give me the total current, right, contained inside this loop, modulo of fundamental constant. And the line I'm drawing here, the Amperian loop, please note that it is this loop. It goes through the donut. It goes through the center of the donut. It's the filling of the donut. Okay, it goes, that's the loop that I choose. You can choose another loop if you want, but this is the easiest loop. Okay, because we need to determine the B field inside this, right? We need to determine the magnetic flux, okay, to determine the inductance. To determine the magnetic flux, we need to know the magnetic field, right? Because the magnetic flux is magnetic field integrated over the area. Okay, so if you go through this exercise, you will find that integral of B dot ds is just integral of B ds cosine 0 degrees. Why cosine 0 degrees? Because the B field is pointing in the same direction as your path of integral. Okay, your B field is also going along this toroid. Okay, hopefully you guys remember the solenoid, right? The solenoid is a loop that. Okay, a solenoid is a loop that looks like that, right? You have a lot of loops, and I don't draw it completely, you know, right? It's a lot of current, and in a solenoid, the B field will be pointing in this direction, highly concentrated here, and very weak outside. Right, so the same case, this is just like a solenoid that you twisted around, right, to form a circle. So, you're going to have a concentration of B fields inside this donut. Okay, and it's going to be pointing in the same direction as this Amperian loop. Okay, so the angle is 0 degrees, which is convenient. That's why we choose this Amperian loop. Because it's convenient, it makes it a very simple integral to solve. V integral ds is simply V times 2 pi r. Because 2 pi r is the circumference of this circle, right? It's the entire length of this circular path, this circular Amperian loop. Right? And I set it to be equal to mu naught ni because of Ampere's law, right? Ampere's law tells me that integral V dot ds must be equal to mu naught I, right? Where I is the total current. Here I got replaced by Ni for the same reason as the previous question, right? Because you have n loops, so each loop is carrying current I. So the total current that's being enclosed, right? this is carrying current I, this is carrying current I, this is carrying current I, I can slowly count, okay? I can slowly count until midnight tonight, okay? But there will be n of them, okay? Enclosed inside this circle, right? Inside this green circular count, right? So that's why the current gets Ni. Okay, and as a result, I find that my B field is given by mu naught Ni over 2 pi r. Hey, that looks the same. That looks like the B field of a wire, right? Of an infinitely long wire, okay, located at this location. Right, but it's a different problem, same formula but different problem. Okay, so don't be thrown off by that. Okay, so B is equals to mu naught 2 pi r, right? Where r equals 0 here is taken as the reference point. Okay, r is, or rather this point is taken as r is equals to 0. Okay, so depending on the distance, okay, this diagram actually illustrates it very nicely. R is basically the distance from the center of the donut to wherever is the inside of the donut you're interested in. Okay, that's the definition of R. So very good. We have the formula for the B field as a function of R. And now we need to integrate the flux. Okay, as we recall, the flux is simply B multiplied by the area, but in this case, B is changing as a function of position, right? So the multiplication generalizes to an integral. Okay, B dot dA, and very fortunately for us, B is in the same direction as A. Why? Because the area A, right, the vector corresponding to the area A is pointing out of the page. Okay, actually it's either in or out of the page, but for magnetic flux, we only care about the magnitude. Okay, we don't care about the sign. Right, so we can just treat it to point the same direction as the B field, because the B field is also, right, if I'm assuming that the current is flowing this way, then the B field is also pointing out of the page. Okay, so I have integral B dA like that. Do I know what capital B is? Yes, I do. It is simply mu naught Ni over 2 pi r. Do I know what dA is? Right? Yes, I do, because dA is given, dA is a very small rectangular section whose height is given by h and whose width is given by dr. Is this, let me use red color, the color red. Okay, this is dr. Okay, this is dr. Okay, dr. Right, this tiny segment. Okay, so we can see that HDR gives me the area of this infinitesimally small shaded rectangle. Okay, that's why dA over here is given by HDR. And after you have reached this point, physics is over. Okay, right? You have, it's now a mathematical problem. You now need to solve this math integral, which fortunately is very easy to solve because integral of 1 over r is simply the natural logarithm. Okay, and therefore we have an expression for phi b. Okay, in terms of all of the quantities over here. Okay, any questions about this process? Okay, we are not at the end of our solution yet. We still need to apply the definition of the inductance. Okay, inductance is total flux over I. Once again, do not forget your factor of n, because your flux phi b corresponds to the flux for one loop. But you have n loops, right? You can count 1, 2, 3, 4, 5, 6, right? N loops in total. So the total flux is n phi b divided by I. That's the definition of inductance. And the current I cancels out in the numerator and denominator. So you don't even need to know what it is. Okay, and indeed, you know, since inductance is a fundamental parameter, it should be independent of current, right? Otherwise, it's very weird to have inductance that is. I mean, it's very weird for this problem, you know. In real life, of course, everything changes a bit when things change, right? So, yeah. Okay, so here is our final expression for the inductance, okay? And all that is left is to substitute in the numbers in the problem to get 91.2 microhenries. Okay. Okay, and that's it for today's tutorial questions. Okay, are there any questions? Would someone like us to revisit any earlier questions? either in this tutorial or in previous tutorial.
That's my question.
Okay, if not, then thank you very much, guys. I won't see you again for tutorial, but I will see you in lecture, I hope. Okay, thank you. Have a good week.
Because after EM, this is see you in lecture. You ask him, you want to care.
Alright.